Yeah, okay. Good afternoon, everybody. Thank you for still joining in this Zoom. And in this session, we will continue our presentation with the title of the design and control of microgrid with Typhoon. I think in here we have Mr. Marcus Lim, which ready to present this presentation. And as maybe after this session, we will have another presentation from Dr. Ronnie, which will present about how the utilization of Typhoon HIL for developing the lecture, teaching, and lab modules. Okay, now we will give the time for Mr. Marcus for presenting your presentation. Please, Mr. Marcus, thank you very much for your attending this session.
All right, thank you, Dr. Shodaya, for your invitation, and thank you for the MESfIA committee for having me here today. Actually, I'm very honored to be able to present to you what Typhoon Hue can do in the design and the development of microgrid systems. Okay, so a little bit about myself. I am based in Singapore and I represent Typhoon Hue. Typhoon Hue is a company based in Europe, right, with offices in Switzerland and Serbia. So we represent Typhoon Hue in Southeast Asia. And it was our honor that UGM procured a Hue system, okay, for their project, for the development of the microgrid curriculum. So I will now begin with my presentation. So let me share my screen. Okay, so I'm just going to give a very quick introduction on what hardware in loop is and how you can use it for the design of the microgrid system. Okay, HIL stands for hardware in loop. All right, in loop means that it uses the hardware emulator. All right, and it does the emulation in real time. So HIL has been around and it's been used throughout the world for the simulation of power electronics, power system, for microgrids, for electric vehicle, which is also a very big market for or big applications for HIL. Now, so let me begin, all right, by telling you the scenario. So currently, the modern power electronics design it's quite challenging. Why? Because the grid is becoming more dynamic. You have a lot of energy resources, like Dr. Sudamono presented, right? He has the PV, he has the diesel genset, he has the BESS, and they all need to be working together in real time. So because of that, it is becoming dynamic. The controller must be able to allocate the resources quickly, all right, to prevent the grid from collapsing. So at the heart of all these power electronics are the power electronics converters, the AC-DC, DC-DC converters, and the inverters. And these inverters are actually found in all the various PV, all the controllers. So all these inverters are also being controlled by smart controllers. Now, and because of that, all right, a system like this, a microgrid system like this will have many controllers in the primary. So maybe in the wind area, they have an inverter. The inverter has a controller. In the solar, the PV farm, the PV farm has a controller. So there are many primary controllers, and then there is a main controller, a microgrid controller or a hybrid controller that controls the flow of the energy between the different energy resources to the loads. Okay, so all this needs to be happen properly, otherwise there will be trouble in the grid. Now, so how do you ensure that the system that you design is done properly? So in the past, what you do is that you will use a software simulation, all right, MATLAB, maybe PSIM, and then you will design your circuit and you will run your simulation, okay? But this is software simulation. While it is low cost, it is easy to use. It is not, the fidelity is not high, okay? Because you cannot really simulate or the real-time faults, okay? And you cannot connect your controller and test it robustly. So after you're done with your software simulation, the next thing that you do is that you will create a hardware prototype, okay, to test. Now, but the hardware prototype itself has its problem. First, it is costly, all right? To build a whole microgrid system is costly. Although it gives you a very high fidelity, it is not cheap. And also, for a real hardware prototype, you cannot test multiple fault scenarios. Okay, you cannot test LVRT. I mean, you can create certain test scenario, but you cannot test all of them because the hardware is very inflexible. So what can you do to be able to combine the best of software simulation and an actual hardware prototype? That is where hardware in loop comes in between here. All right. The hardware in loop actually, we have at the heart of it is this hardware emulator. This hardware emulator will emulate the power stage, okay, and run it in real time. And then you can connect your controller to it, and then you can simulate it. Now, because it is running in real time, the fidelity is very high. But at the same time, because it is running on FPGA, you can always test different fault scenario without having the high cost or without it being dangerous to the tester itself. So further introduction to hardware in loop. Okay, so what is hardware in loop? Hardware in loop, right? It emulates power electronics at very high fidelity. Okay, so it will emulate your PV module, it will emulate your inverters and your loads. It will emulate them in this box. Okay, it's the actual replica of physical system, but it replicates it digitally in this box. Then now in this hardware in loop, it is running at a very fast processing speed. Okay, so the simulation time step of Typhoon Hue can be as little as 0.2 microsecond, 200 nanosecond. So if it is so fast, right, when you connect it to a controller, the controller will think that it is actually controlling a real power stage. So it will be able to test and run it like as if it is running an actual plant. Now, but because of that, you are able to test your control logic, your firmware, and your actual controller in real time without having to build expensive prototypes or labs. Also, because you can always you can design in different fault scenarios, you can test different scenarios and see how your controller responds in real time without risking a catastrophic damage. So hardware in loop simulation is used for inverter control. All right, so this is an actual inverter you emulate inside the hardware in loop, and then you connect your controller and then you run it in real time to test it. Or on a bigger system, you can actually do a microgrid control. You can use it to emulate an actual microgrid system and then run it in real time. Okay. So now there are many HILs in the market. I'm not sure if you heard of Oppo RT, D-Space, SpeedGoat. Typhoon Hue is one of the HIL manufacturers. Okay, but we are specifically targeting at the power electronics and microgrid arena. Okay, what makes our technology different is that inside the Typhoon Hue, we use a field programmable gate array, FPGA, for real-time power electronics simulation. FPGA, so there are two ways to do processing. One would be CPU, the other would be FPGA. So we are using FPGA because it is faster. Okay, it allows you to do parallel processing. So it is able to simulate the real-time power transients, okay, the dynamic transients accurately with high fidelity. So it's real-time. And also FPGA is reconfigurable, meaning that you can always change your design, all right? Inject different scenarios and then see how your controller behaves. We also have ARM cores. Besides the FPGA, we have ARM control cores inside for users to program their controller. Okay, and then we have multiple input and outputs to interface with the Hue itself. So how accurate is Typhoon Hue? Now this is just a very simple testimonial, okay, example. This is a lab in ABB, all right? And and they were testing a 4.5 megawatt full-size converter. We converted all of this into digital format and loaded into the Typhoon Hue. And then we run them side by side to compare the results. So in steady state, you can see that the actual the waveform from the lab and the Typhoon Hue's waveform are evenly matched. Okay, they are close because it is real-time processing, so it is actually close to the fidelity is really high. Now, how do you use a Typhoon Hue? Okay, so I will use a very simple example. Let's say you are designing a controller to control a grid tie inverter. Okay, and this grid tie inverter, this is a DC source, so it could be a PV module. Connect to your grid tie inverter, and then your grid tie inverter connects to the grid. So this portion is where you will be, this is where the the controller algorithm is. You will emulate the power stage and put it inside the Hue hardware. For this algorithm, you will load it into your controller. Okay, this is your actual controller, and then you connect the controller to the Hue, and then it will run it in real time. Okay, so the dangerous portion, all right, the high power portion is emulated here, and then you connect your actual controller so you can run it in real time. So in that way, you can run it in high fidelity, but also safely. Okay, so we are able to connect to all controllers. We are controller agnostic. Also, you can, if you do not have an actual controller, you can build your controller and put it inside the ARM processing cores inside the Typhoon Hue. So in this example, you have a PV module that a PV cell that goes through a boost converter and charges a battery and sends it to the load. Okay, so you can, this portion is designed and emulated in the Hue hardware. And then you connect your controller sends the PWM signal to the converter. At the same time, it reads back the voltage and current measurement, okay, so that its MPPT algorithm can adjust the PWM accordingly. Okay, it will also monitor the state of charge. All these measurements at the PWM is sent through the input and output ports here. Okay, so in that case, you are able to perform a closed loop simulation. Right, it is not a simulation actually, it's a real-time test, okay, with your actual hardware. Now, you may, if let's say you do not have a hardware, then you can actually run the controller algorithm inside the Hue. Because the hardware, the Hue, the Typhoon Hue itself has ARM cores that you can run your algorithm inside. So there are two use cases here. Either you use your actual controller or you use the controller that is inside the Hue itself. So this picture summarizes the value, all right, of hardware in loop. It is more accurate than a software simulation because the software simulation makes use of the computer's CPU, right? And the CPU itself is sequential. So it is slow, all right, and it is not able to emulate the dynamic transients as quickly as it should be to test your controller. Also, so if let's say you have a controller and you connect it through the USB port to the software, okay, we call it software in loop. That is too slow to really robustly test your controller or your control algorithm, okay? Now, if you build a hardware prototype, well, it is accurate, but it's expensive and it's not flexible enough to test different fault scenarios. So the hardware in loop falls nicely in between the two ends of the spectrum. So what applications can you use with Typhoon Hue? Well, like I mentioned, you can use it for inverter and controller testing, inverter and converter controller testing, okay? So what you do is that after you have designed it and you connect it to your controller, you can run the simulation, and we have widgets for you to monitor every point in your power stage. Okay, we have a built-in oscilloscope. We have gauges for you to read out. Okay, and you are able to create different types of fault, LBRT, all right, HBRT, the fault duration, and see how things behave. So now this is an example of how you can, we also have the PV curve where you can monitor how well your MPPT algorithm in your converter behaves, whether it's able to extract maximum power from your PV cell when the sunlight changes because of cloud cover, because it's evening time, right, throughout the different times of the day, as well as the temperature changes. So not only you can design and test in real time, you can monitor, all right, your design, okay, and see how robust your controller is to respond to changes in the faults. So we have a series of hardware Hue emulators, ranging from the small one where you can test a simple three-phase inverter, to a huge one like what UGM has got, the Hue 604, for large-scale grid simulation. Okay, you can test 8 switching three-phase inverter model. What that means is that you can test a microgrid. All right, the microgrid could have PV, wind, diesel gen set, BESS. All right, and each of it has a three-phase inverter in it. Okay, and you can test 8 of those in parallel. Okay, so you can form an entire microgrid system and see how it works. So later we will look into it in greater detail. So this is the key point of this from where I was starting. After you have with the Typhoon Hue, you can actually connect with other peripherals, okay, or you can run it on itself to emulate a full microgrid system. Now, as you can see in the microgrid, right, you have the PV arrays, and then you have the inverter. Every inverter has a C. What does this C means? Okay, basically C means controller. Every inverter has a controller, all right? Controller is the heart of the microgrid system. I could say that, all right? Because so the controller itself, this is what we call the primary, because interface directly to the PV, but above all this little primary controller is the main controller, all right, the microgrid controller that controls the power flow between the different energy resources and the loads. Now, the main microgrid controller or the hybrid controller, right? We have different names for it, but the top level controller, it must be able to respond to different scenarios, okay? Whether is it islanded or if let's say it's connected to the grid and suddenly there is a disconnection to the grid, it must be able to perform in islanded mode, okay? How to make one of the energy resources form the grid rather than follow the grid. It must be able to handle different protection relays. Okay, it must be able to communicate using the protocols, Modbus, IEC 61850. Okay, it must be able to handle different faults. Okay, so all this needs to be tested robustly. Okay, now if you build an actual microgrid system, it's very hard for you to test all this. It is also very dangerous. It is also very expensive. If you run all these tests in the software, it is just too slow. So the best way is to run it on a system that actually runs the test in real time, but in a safe voltage. Okay, so you can test the fault scenario without harming, okay, without causing the entire grid to fail in a safe environment, but also at very high fidelity. So this is what I mean, all right, the Hue microgrid test bed. You can see that there is a top level microgrid controller controlling the different controllers of the different converter. So in a microgrid controller, a microgrid system, you may have PV, you may have battery, okay, you may have wind, you may have diesel genset, and each of them have their own controller, and they all is being controlled by the top level supervisory control. Typhoon Hue is able to test from the top all the way down the bottom, okay, at different layers of the stage, okay. So I would imagine in your research, if you are researching on grid tie inverter, so you are just focusing on this portion, you can use Typhoon Hue to do that, okay, to see basically you can work on your MPPT algorithm. Now, if you are working at this level and you want to see the overall view, Typhoon Hue is able to emulate the entire system, and then you can test your microgrid controller algorithm, okay, as well as the communication protocols. So I think this would present a better view. Okay, so in this example, this is an example of a microgrid. So in this microgrid, you have solar, you have battery, you have wind, okay, and they are all connected to an inverter and then connect to a point of common coupling. There is also a diesel genset. At each point, there is a relays, okay. So this relays, you can either design it inside. So whatever that's inside this red dotted box is emulated inside the HIL 604. Okay, that is the same one that UGM has. Now, so all this is emulated here, but besides emulating it in the Typhoon Hue itself, the hardware itself, you can also connect real controllers to control the DER, and you can connect actual inverters here, all right, to connect to to test the real relays. Okay, so this can be a hybrid of some sort. Some of the relays are emulated, some of the relays are real actual relays. Okay, so there is a hybrid of both sorts. This allows you to fully test your microgrid control. Okay, so this is just a blow-up example of how you can use Typhoon Hue all right, to perform microgrid research and development. So to be clear, this is the PV, and yes, the inverter. The inverter needs to be controlled. So you can use an inverter controller for it. Now these have relays. You can connect to real relays, or you can emulate the relays. Okay, and then this microgrid controller is your secret sauce, right? You design the controller, and then you make sure you want to test how well it's able to allocate the or direct the energy flow between the grid, the energy resources, and the load. Later we'll see this in an actual Typhoon environment. Okay, so these are what we call besides the Typhoon Hue, these are what we call the peripherals. So we have different peripherals available, protection relays, grid controllers, okay, genset controllers that can connect to the Typhoon Hue to make it an actual test bed. Now, simulation will not be useful if you are not able to view your simulation in details. So Typhoon environment provides a SCADA, just like how an actual SCADA of a microgrid would look like. Okay, so they have different SCADA panels where you can view the power consumption, all right, the power flow at different points in your design. So perhaps a good example would be to show you a model of a microgrid system in Typhoon Hue. Okay, so I'm going to show you the Typhoon Hue environment here. So this is the Typhoon Hue environment, and this is where you design where you do your design. So just a little introduction. This is a model of a microgrid. On this microgrid itself, all right, there are 4 energy resources. You have the BESS, all right. You have the wind, you have the PV, and then you have the diesel genset, all right. It is quite similar to what Dr. Sudarmono presented just now about his microgrid in Karimun, all right, except that he didn't have the wind, all right. He has a PV, he has a BESS, diesel genset. This is what when he presented the high level penetration, all right. Now in these 4 energy resources, okay, is also connected to the national grid. Okay, so this microgrid now, so this 4 energy resources is connected to the microgrid to the national grid through a PCC, point of common coupling. Okay, and the microgrid itself is used to serve the different loads. You have a constant load, you have an interruptible load, variable load. Constant load will be load that is always there. All right, there's always a baseline load condition. Variable load could be different, you know, sometimes in the evening when people start to take hot water showers, okay, the energy resource goes up. So these are the different points. Now, at the heart of this entire microgrid is this microgrid controller. This microgrid controller, okay, has to make sure that, you know, when it is connected to the grid, okay, all these 4 will follow the grid. If let's say there is a cut in the connection to the grid, then it must be able to allocate one of them, all right, basically either the battery or the diesel genset to form the grid, all right, and support the grid in the microgrid in islanded mode. Now, each of this, this is a top level view, okay, and if you go look underneath it, this is actually a battery and an inverter. Okay, so this battery is a lithium-ion battery bank, and then you have the inverter. Now, the inverter itself has a controller. So this is from the battery. So the battery is a DC, And then there's a three-phase inverter that converts from DC to three-phase AC. All right, this inverter has a controller. So this is the primary controller that controls the inverter. All right, so I'm going up right now. So it's the same with the wind, the PV, and the diesel genset. All of them has so this is the diesel genset. All of them have the inverter, have a control. Okay, so like I said, control is everything in microgrid. Okay, and because it is so complex, it is best that you have a thorough real-time high-fidelity simulation before you implement it into the actual system. So besides the primary microgrid, primary controllers, then you have the top level, highest level microgrid controller. All right, the hybrid controller. So this is where your algorithm resides. Okay, you could return it in C code. Now in this example, everything is running on Typhoon Hue, both the inverter and the controller itself, because like I said, you have an option of programming the ARM processor, the ARM CPU inside the Typhoon Hue to perform control. All right. So so once you have modeled this, you can simulate it, and after you have simulated it, okay, you can run it in a SCADA. Okay, so in the SCADA, you are able to, for example, cause a fault on the grid, okay, and then see what happens. And then you can see the various battery inverter readings. Okay. So you see, once there's a fault, all right, the battery is supposed to inject active power, all right, and reactive power, sorry. Okay, and you can see what happens when there's a fault, all right, there's a drop in the frequency, a frequency drop. So this is very useful. We also have an oscilloscope view for you to see the different waveforms. What happens if it runs the diesel genset, all right, then the diesel genset will start to spool up, all right, get synchronized with its frequency before the contactor circuit breaker turns on. So this is how you can thoroughly test your microgrid. Now, bear in mind that right now I'm not running this in real time because I'm not putting this in an actual Hue hardware. I don't have a Hue hardware right now with me. Okay, so it is right now running on software, so it's pretty slow. But if you run it on Dr. Sajia's and Dr. Ronnie's Hue 604, it will be very fast. This will be real time. Okay, so how do you know whether is it real time? You look at the clock here. Okay, now if you run on the Hue, then this, if you use your watch and you look at here, okay, it will be the same time. It is running in real time. Every second is true. So here I'm running in virtual Hue mode, so it's a bit slower. So it takes a while before it simulates 1 second of data. All right, so this is like a software simulation, but in the Hue's hardware simulation, this will be running at the same time as your watch. Okay, a real-time simulation. All right. So okay, so this is the microgrid SCADA on Typhoon Hue. So it is very useful. I mean, it is very useful for researchers, microgrid researchers, and developers to invest in the Hue. Okay, because of its flexibility. It is flexible, yet it is accurate. Software is flexible but not accurate. Hardware is accurate but not flexible and expensive. So a Hue is actually the best middle ground. In power electronics industry, they are heavily using Hue. Okay, our Typhoon Hue is used in many both in the industry and the academia. Okay, so you can also connect the Hue to actual power amplifier. All right, so to run full power test. Okay, because the Typhoon Hue itself, the I/O is plus minus 10 volts, right? But let's say if you want to test a converter that is running at 800 volts, then we are able to provide power amplifiers for you to interface your Hue with your converter. So this is actually a DC-DC converter. So you just need a 2-quadrant power amplifier that provides a source and the sink, because this is a bidirectional converter. But if you have a 3-phase converter, then you want to test it, then we will provide you with a 4-quadrant 3-phase power amplifier. Okay, so this one, it will be able to source and sink and interface with the Hue, all right, in 3-phase, okay, AC and DC. So, like I said, the Typhoon Hue is used widely in the industry. Not just Typhoon Hue, but hardware in loop in general. Okay, it's used widely in the industry, but I will now talk about some of our customers that have used Typhoon Hue and what they do with it. Okay, so ABL use it to simulate, all right, their EV drivetrain in their cars. Okay, IHI, they make controllers for BSS controllers, all right, and they make use of Typhoon Hue to do their simulation. Okay, Southern California Edison, they partner with ABB to create a microgrid, but before that they use Typhoon, right, to perform testing, validation of their controller before they test it on their actual grid. Now in academia, we have universities in Thailand. This is in Malaysia that uses Typhoon Hue, and right now in Indonesia, UGM has a Typhoon Hue, okay, which we are very proud of. And so Typhoon Hue has been used in many universities for academic research itself. Okay, our largest one would be in MIT, Lincoln Labs. Okay, so this is where they also presented the this is where they presented the feasibility of using hardware in loop to do actual microgrid testing. Okay, for actual microgrid testing. Yeah. Okay, so this is the microgrid test bed at MIT. All right, it models a diesel genset, solar plant, battery. It models 40 over relays, okay, 50 circuit breakers. Now, some of it, they use rail controllers. So this is a pretty big system. Some of it, you can see this is the EPC power controller, Woodward genset controller, rail relays. So some of the relays are rail relays. Some of the relays here are software emulated, okay, on the Hue. Okay, and they are controlled using, there are 2 protocols that they use, all right, Modbus TCP and IEC 61850. I guess because of the differences in the different implementation. And they are able to get a time resolution, a simulation time resolution between 1 to 4 microseconds. So it's very accurate. Okay, that kind of time step, an actual controller would know it's controlling a hardware in loop. It will think that it's controlling the real plant. Okay, so this is where it is very useful. So in summary, Typhoon Hue and Hue in general provides a brand new way to test and validate various power electronic systems. Hardware in loop has been used in the industry for a long time, but it was expensive. It was used to model jet engines, okay? But right now with FPGA technology, cost has come down and also the power electronics has become more control-based, so it's a good fit. What is important is that it's highly accurate. Why? Because its simulation is in real time. And then it is also very flexible. So it allows a wide variety of use cases to be tested. So if you are interested, you can drop me an email, or you can go to the Typhoon website to check it out. And Dr. Ronnie later will present on how he will develop modules using Typhoon Hue, right, for study. So that's my presentation. Thank you very much.
Thank you very much. Thank you very much, Mr. Rasmus Lim. I think very impressive translation to explain how Typhoon hardware in the loop can be used for the design, control, simulation, and it's already has been used in many institutions. Please, Prof. Antonis, if you have any comment and question.
Yes, I would like to thank Dr. Lim for this interesting presentation, and I would like to ask up to what extent Typhoon can cooperate with smart grid solutions that are more hardware, like the ones of solutions from companies like Edibon, Lucas Nulle, and De Lorenzo, and so on. How this equipment could cooperate with the Typhoon hardware in the loop emulator machine.
Okay, thanks, Dr. Anthony. Yes, it is. So Typhoon is very flexible. I know that just now you have presented De Lorenzo's emulators, right? And you could actually design a portion, all right, of the. There are two ways to look at it. Number one is that you can design a portion of the power stage, and then connect directly to the rest of the systems that you have using the I/O. All right. Typhoon has interface boards that allows you to do that conversion. We mentioned about power amplifiers. All right. You could use that to bring up the voltage level. Secondly, you can also design your control algorithm inside Typhoon Hue and connect to the different modules that you already have. So it works both ways. Typhoon can work alone, but it can also cooperate with the equipment and the modules that you already have. So if you're interested, so it can get quite detailed in that, but we are really open to exploring this cooperation. We can provide advice, consultancy on how we can have a good fit, right, with the items that you have and with Typhoon.
Thank you for your information.
My pleasure. Thank you.
Yeah. Okay. Maybe any other question from the other participant? Okay, please, Mr. Alexandros.
Yep.
Paspatis.
Hello, I'm Dr. Paspatis from the HM Grid. Thank you for this nice presentation. I would like to ask Dr. Lim, what is the state of the connection of the Typhoon HIL with the Simulink software? And I'm aware that Typhoon has been working on integrating these two solutions in order to speed up the testing, especially in areas like power electronics, where Simulink is very famous. So
yes.
Are there any news with this, and how is it going?
Yes, I'm glad you asked this question because I had one slide that showed the integration. Maybe I quickly share that. So recently, Typhoon has integrated or developed a way to perform the integration of Simulink designs and run it directly on the Typhoon Hue itself. It uses a functional mockup interface. Okay. I will send the link on the chat group. So using this, you can using the Simulink. So after your design, you can convert it into FMI, okay, functional mockup interface, and then you can export the controller code directly to Typhoon Hue itself. So this is one example. The other one, if let's say you're using PSIM, it is even more seamless because PSIM and Typhoon Hue, they had a joint project to integrate each other's environment. So in PSIM, you have a button that will export everything into Typhoon Hue, and on a Typhoon Hue environment, you can import it direct. You can import the file directly from PSIM. Okay, so I will send you more details on how you can do this integration from Simulink to Typhoon Hue. So this is the functional mockup unit, and we are still improving as the days pass. Okay.
Thank you.
Welcome. So let me get this check.
Question and comment. Any other question? We still have 4 minutes more. Yeah. Okay. There are no more questions. I think this presentation can be end. And thank you very much for Mr. Marcus for very interesting presentation and sharing. If you have any other question and comments for Mr. Marcus, I think you can send email to Mr. Marcus directly. Thank you very much again for Mr. Marcus. You can applause.
Thank you, Dr. Hajjai. Thank you, everyone.
Thank you.